Hello again, Math 10Cs. In today's lesson, we are going to start a new unit of study with the name of the new unit being Relations and Functions. And we're going to do so just by reviewing material that you're already familiar with back from junior high math. So we'll do a little bit of a review of a Cartesian plane and just how to plot points. And then we'll look at constructing some graphs and then distinguish between what it means for data to be discrete or continuous. So let's skip over all of this. I don't need a history lesson about the Cartesian plane. Okay, so jumping straight down to the first example, it says complete the following by writing the coordinates of the points represented by the letters on the grid. Okay, so when we write down points, we want to take these points, we want to identify their position on the Cartesian plane. We do it in the form of an ordered pair. So an ordered pair has your x-coordinate first and your y-coordinate second. So what this would look like is, so if we start with a point A, I would identify where point A would hit the x-axis. So it hits the x-axis from the origin, you go 0, 1, 2, so you'd have 2. And then it hits the vertical axis, the y-axis, at positive 4. So that point would be 2, 4. And then point B, well, point B lies directly on the y-axis, or the x-axis, and it lies on the x-axis at a value of negative 3. And in terms of like where it would hit the y-axis at, it would hit it at 0. So you'd have negative 3, 0. Point C would hit the x-axis at, looks like 6 here. So you got 6. And then if you go over to the y-axis, it would hit the y-axis at negative 3. Or not negative 3, negative 3. Check that. 1, 2, 3. Yeah, negative 3. Point D, if you identified where it is on the x-axis, if I draw a line right up to the x-axis, it would hit it at 0. So it's an x-coordinate of 0. And its y-coordinate is, well, it's already on the y-axis, so it would have a value of negative 3. And then we have point O, and that's just the origin. The origin would have a coordinate of 0, 0. So my points are 2, 4, negative 3, 0, 6, negative 3, 0, negative 3, and 0, 0. Okay, it says write the coordinate that's in the second quadrant. Okay, so the way that we label the quadrants is as follows. This top quadrant is what we call quadrant number 1. The top right quadrant. The top left quadrant would be quadrant number 2. Bottom left quadrant is quadrant number 3. And bottom right quadrant is quadrant number 4. So it says write the coordinates of the point in the second quadrant. The only point that's actually in the second quadrant is point E. And point E has coordinates of, well, let's check this. It goes down to the x-axis here. So that hits the x-axis at negative 2. And then it would go across the y-axis at positive 3. So it'd be negative 2, 3. Write the coordinates of the point that's in quadrant number 3. Well, that'd be point F. So point F, you go to the x-axis, it would hit it at negative 4. And if you go across to the y-axis, it would hit it at negative 3. So you'd have negative 4, negative 3. And it says complete the following table to identify whether the x or y coordinates are positive or negative depending on which quadrant you're in. So if you look up here, quadrant 1, every point would hit the x-axis, the positive x-axis and the positive y-axis. So this would be positive and positive. Quadrant number 2, that's like point E. So point E had a negative x-coordinate and it had a positive y-coordinate. Quadrant 3, so that'd be point F. That has both a negative x and a negative y-coordinate. And then quadrant 4, that'd be point C. So point C would have a positive x-coordinate and a negative y-coordinate. Okay, so that's just a little review of your different quadrants in a Cartesian plane and how to plot the points. Okay, now we're going to look at a pattern of toothpicks. So it says you have 3 toothpicks are used to form a triangle. And a second triangle is formed by adding 2 more toothpicks. and a third triangle is formed by adding even more of them. Okay, so for example, in this picture here, this first triangle has 1, 2, 3 toothpicks. This second shape in the pattern has the first triangle, so you have 1, 2, 3 toothpicks, and you add 2 more of them, 4 and 5. You only need to add 2 more toothpicks to get another triangle because you have one side that's being shared between the two. And then shape number 3, you have 1, 2, 3, 4, 5, 6, 7. So you add another 2 of those. Okay, so it says the first thing is to draw the next 2 shapes in the pattern. Okay, so let's start off with this shape over here. So that would be, you have a triangle, 1 triangle, 2 triangles, 3 triangles. So the next one would just be, we'd add another 2 toothpicks to form another triangle. So 1 here and 1 there. And then the next shape of the pattern would be, we just add on to this one. So we'd have a triangle, another triangle, third triangle, fourth triangle, and then we just add the 5th one here. Okay, so that'd be like my shape number 5. Complete the table relating the number of toothpicks P. Okay, so we're going to use a variable to represent the number of toothpicks. That's P. To the number of triangles, we're going to use the variable capital T to represent that. Okay, so if you look at the pictures up here, so this first shape has 1 triangle, and it has 3 toothpicks in it. This second shape has 2 triangles, and it has 1, 2, 3, 4, 5 toothpicks. This third shape has 3 triangles, and it has 1, 2, 3, 4, 5, 6, 7 toothpicks. And we could count the number of toothpicks in these last two pictures here, but at this point you can see a pattern. For every increase in 1 triangle, we're adding 2 toothpicks. In fact, they even told us that up here. It says we just keep adding 2 more toothpicks. Therefore, we don't even need to count. We can just simply fill the pattern in. So this would be 9, and this would be 11. Okay, now it says represent the data from the table of values on the grid. Okay, so we're just going to plot these points. So the x-axis we're going to use to represent the number of triangles, and the y-axis is going to represent the number of toothpicks. So the way to plot this is we basically would plot the number of triangles as your x-coordinate and the number of toothpicks as your y-coordinate. So for example, when you have 1 triangle, you would have 3 toothpicks. So if we plot that, this would be, well, first of all, let's make a scale. So let's make a scale that starts at 0 and we go up by 1, 2, 3, 4, 5, 6. And then this one we can go up by 1, 2. We can label every second grid line just to save some space, but I'll do every single one labeled here. Okay, 7, 8, 9, 10, 11. Okay, so if we plot these points now, 1 triangle has 3 toothpicks. So I'd start out 1 triangle has 3 toothpicks. So that's going to be plotted right here. 2 triangles has 5 toothpicks. So at 2, we go all the way up to 5 here. At 3 triangles, we have 7 toothpicks. So it'd be 3, 7, which is up here. And then we have 4, 9. So 4, and then all the way up to 9 here. And then go up even further, and we have 5, 11. So 5, 11 will be plotted all the way up at the top. Okay, it says explain why it does not make sense to join the points in a straight line. So the idea right here is if you look at the different points, they form what we call a linear relation, just because I could potentially put a straight line through these points. But the thing is, it actually doesn't make a whole lot of sense if you do this. So I'm just going to draw a dashed line that kind of goes through here just to show that we're not actually going to put a solid straight line through it. So if I did a dashed line that went through, okay, it would look something like this right here. Now, what this means is that if you have a line that goes through all these points, it means that you could look at any point on the line and it must make physical sense. So let me take an example of a point that doesn't make any physical sense. So let's look at what would happen if you had, let's say, 4 toothpicks, okay? So if I have 4 toothpicks and I go over to the line here, and then I went all the way down, this would mean that when you have 4 toothpicks, you'd have 1.5 triangles. It doesn't make any sense. It's either you have a whole triangle or you don't. You can't have half of a triangle. So this is the issue. So let's just identify this. So I'll say a continuous line would indicate you could have a value at, for example, we'll use that point that I identified. So my point was it would be 1.5, comma 4. But the problem is you cannot have 1.5 triangles. So it actually doesn't make any sense to draw a continuous line through here. A dashed line would be okay, just to kind of show that like the relationship is linear, but like you can't actually have in between points. Okay, E says describe in words the relationship between the number of toothpicks and the number of triangles. So what's basically saying is like if you took T, the number of triangles, what would you do to T to get the total number of toothpicks? So think about this. We go back up to this data table here. If I start with the number of toothpicks, what am I doing to that number to get, sorry, if I start the number of triangles, what am I doing to that number to get the number of toothpicks? If I start with the number of triangles, what am I doing to get the number of toothpicks? Now, you might need to think about this for a moment, but I'll simply identify what the relationship is. If you double the number of toothpicks, and add 1, you get the number of, oh, sorry, double the number of triangles, not toothpicks. Let's change that. You double the number of triangles. We can use the variable t to represent that, so capital T. Double the number of triangles, T, and add 1. You get the number of toothpicks. I'm using P to represent that. Okay, F says what's an equation that can be used to determine the number of toothpicks if we know the number of triangles? Well, we'll just take our complete sentence up from part E and just write a mathematical equation. So basically, if you take the number of triangles and you double it, so that'd be multiplying by 2, and then you add 1, that would be equal to the number of toothpicks, which would be P. But let's rewrite the equation so we have P on the left-hand side. And also here, if we have T times 2, we can write it as 2 times T. So we could write down 2T plus 1 is equal to P. And then P would be equal to 2 times T plus 1. Okay, that's my equation I can use to figure out the number of toothpicks from the number of triangles. Again, you can confirm that just by taking a couple of points here. If you double, for example, the number of triangles, that would be 10. Add 1, it gives you 11. If you double the number of triangles here, which would be 8, add 1, you would get 9. Now, the power of getting an equation like this is we can figure out the number of toothpicks for a shape that has like tons of triangles that we would normally not draw. There's no way we're going to draw like what shape number 27 looks. And our graph doesn't go to 27 triangles. We kind of depend on depend on an equation to solve this. Okay, so it says 27 triangles. So that means that T is going to be 27. Now, what I'm going to do is in the equation, P is equal to 2 times T plus 1. To figure out the number of toothpicks for 27 triangles, I'm just going to take the equation and replace the T with 27, do a substitution. Okay, so if I do that, this would then be P is equal to 2 multiplied by 27 plus 1. If you carry out the order of operations, 2 times 27 is 54, plus 1 would be 55. So you have 55 total toothpicks in that shape. Okay, if you have 27 triangles. Now 8 says, figure out the number of triangles if we have 83 toothpicks. Okay, so this time around it's telling me something different. It's telling me what the value of P is. So that P is equal to 83. Okay, so if we go to our equation, we'd have P is equal to 2T plus 1. Now, this time around, we're going to replace P with 83, okay? Not T, because we're replacing P with the number of toothpicks. So what this would look like is then you would have 83 would be equal to 2T plus 1. Now, I need to solve for what the value of T is. So this is a simple linear equation. So the way to solve this linear equation is you apply the reverse order of operations reverse order of operations and opposite operations to solve for what the value of T would be. So what I would do is, the reason that T is currently not isolated is because it's being multiplied by 2 and added by 1. So in terms of what do you do first, do you deal with like the 2 or deal with the positive 1? Well, look at the order of operations acronyms, so like BEDMAS, brackets, exponents, division, multiplication, addition, subtraction. Now, the reverse order of operations would tell you go in this opposite direction. So if we go in the opposite direction, the thing we have to deal with first is the number that's being added to T. So I want to get rid of that plus 1. So to do that, I would subtract 1 from both sides of the equation. If you subtract 1 from both sides of the equation, you'd be left with 82 is equal to 2 times T. And now, the next thing we deal with is the division, okay? Multiplication, okay? The 2 is being multiplied by T, but to get rid of the 2, we just divide both sides by T. So divide by 2, divide by 2. Sorry, I know you can't quite see that there, but the 2's would cancel off. And then 82 divided by 2 would be T is equal to 41. Okay, 41 toothpicks. So that one's a bit tougher to solve for because you actually do have to G had the equation already manipulated for the variable I wanted. And then H is you have to plug the number in and just isolate for the variable in the equation. But again, that just goes back to junior high math in terms of how you would isolate an equation like that. Okay, third example, it says students in a physics classroom determine the resistance in an electrical circuit by measuring the voltage in volts when a current, which we're going to represent the variable I in amps, is passed through the circuit. The table below shows the results. Okay, so it says represent the data from the table on the grid. Okay, so let's see here. So the current we're going to put on the x-axis, and the voltage we're going to put on the y-axis. We'll talk a little bit about that later, but basically the reason the current's going to go on the x-axis is because it is something that we'd refer to as the manipulated variable. Now, manipulated variable means it's something that you have intentional control over. So like if like we were trying to figure out the resistance through the circuit, I'd potentially be able to like turn a knob where I could like change the current that actually goes through the circuit. And then the voltage is what we refer to as being the responding variable. And the reason it's called a responding variable is because it depends on what you're doing with the manipulated variable. So if you start adjusting the current, then the voltage across the resistor begins to change. So it responds as a result of those intentional changes with your changing current. Okay, so let's plot this on the graph. Now, there's no way I'm going to plot every single grid line here. Okay, the grid lines are just way too close together. So every single grid line would be what I call a minor grid line. So I'm just going to plot them on every fifth grid line, which we'll call our major grid line. Now, if we look at the graph here, the current has a maximum value of 4. So I want to like plot just on the major grid line. So that would be here, so every 5. And I want to go up by a number that's easy to deal with, and is also going to allow me to plot that largest current value. So the best thing to do right here would be to start at 0 and just go up by 1s. So go up by 1, we go up by 2, or go up by 1, go up by another 1. So 1, 2, 3, 4, and we'd also have 5 here. And we can write down the variable on the sides. We're going to use I to represent current. Okay, that's my current value. Now, as for voltage, voltage goes up to a maximum value of 48 volts. So I need to plot that on there, and I also want every fifth grid line to go up by a nice number. Okay, so if I need to fit 48 volts in here, I think the best number to go up by would be like 10 by every single grid line. So go up by 10, 20, 30, 40, and then we have 50 at the very top. And we can write down the variable just beside this little line here. So we'll write down V for voltage. Okay, now it says let's plot these points on the grid. Okay, so again, the current is going to be your x coordinate, the voltage is going to be your y coordinate. So the first point is going to be 0.5, comma 6. So 0.5 would be directly between 0 and 1, and then 6 would be, every grid line goes up by 2 here, so this would be located at about this position. Okay, then we have 1.5 and 18. So 1.5 would be directly between 1 and 2. And then 18 would be just one grid line underneath 20, because every grid line represents 2. So this would be located right here. And then we have 3, 36. We've got 3 here. 36 would be 1, 2, 3 grid lines above 30, or 2 below 40, because every grid line represents 2. And then got 3.5 and 42. So 3.5 is halfway between 3 and 4. Go all the way up to 42, which would be located right here. And then got 4 and 48. So 4 is here, all the way up to 48. And then this would be located at this position. Okay, so now, so that's part A. We scaled the graph, we wrote down the variables for the axes, and then we plotted the points. Now it says, does it make sense to connect the points to draw a straight line through the points? Now it does here, okay? So first of all, I'll just draw the straight line, and then we'll explain why that's the case. There's no way I can freehand sketch this, so I need to pull a line on here. Okay, so yeah, let's grab a line. Let's make it in red just to make it stand out. And my line would look something like this right here. Okay, and let's go back to the pen now, and we'll explain why this makes sense. Okay, does it make sense to draw the straight line? If we draw a straight continuous line, it means that all points have to make physical sense. Okay, so let's just take one point, for example, and see like what if this would make any sense. So let's just look at maybe what's going on at a current value of 2. Okay, so current value of 2, if we go up here and went all the way across, a current value of 2 amps would mean that you have a voltage of 24 volts. Does that make physical sense? Yeah, sure. Your current and your voltage values can be whole numbers, they can be decimal numbers, so any numbers along the line actually do make sense. Okay, so the key thing right here is like, yes, a straight line makes sense because in between values make physical sense. And the example I used here was when your current is equal to 2 amps. I'll abbreviate amps with a capital A. Your voltage was 24 volts. So yes, an in-between number does make sense. Therefore, you can draw a solid line. C says use the graph to determine the voltage for a current of 2.5 amps. Okay, so what I would do here is locate where 2.5 amps is. That'd be between 2 and 3. And then we go all the way up to our line. Okay, and then from the line, we then go across to the y-axis. And then using the graph, it looks like when your current is 2.5, your voltage would be about 30 volts. By the way, when I use the line to figure out in-between data points, this is referred to as an interpolation of the data. So interpolation is that we're just using a line that's like drawn to best, a line at best fit through these points to figure out kind of like an in-between value. That's referred to as interpolation. Okay, D says write an equation that expresses V in terms of I. Now, the way we need to do this is let's go back up to our graph here and let's identify, okay, how do you go from the current to the voltage? So what am I doing to the current here, for example, 4 to get to 48? Or what am I doing from here, the current, to get a voltage of 36? So what's the common thing that I'm doing to get from 3 to 36 or 4 to 48? Well, you're multiplying by 12. Okay. So we could say here is, we can say multiply by 12, the current by 12, to get the voltage. So 12 times the current I would be equal to the voltage. But we don't need to write down the multiplication symbol. We can just write down 12I is equal to the voltage. But let's write down the voltage variable first. We'd have V is equal to 12 times I. And let's box that. Okay, now it says use the equation to determine the voltage when the current is 6.2 amps. So what I want to do is I want to plug into that equation. I is 6.2. Okay, so my equation is V is equal to 12 times I, and I'm going to replace the I with 6.2. So if you do that, it would be voltage would be, so 12 and the I side by side means we're multiplying, so we'd have 12 multiplied by 6.2, and the units are amps. And then 12 multiplied by 6.2 would be 74.4, and the units are volts here. Voltage is a weird variable. Both the variable, which is a capital V, and the units are actually the same thing as well. Like technically you'd write down V is equal to 74.4 volts. This looks kind of strange just because the variable and the unit are actually the same letter. Although typically you write down a mathematical equation, usually the variables we italicize, so they're kind of like slanted, and the variables we don't show as being italicized. Okay, F says the resistance is calculated from the equation V is equal to I times R. So state the resistance in the electrical circuit. Okay, this is actually pretty easy to identify. So we have V is equal to IR. And our equation tells us that V is equal to 12 times I. So let's just rewrite them. So we have V equals IR. Now, I'm just going to rewrite this equation where I put the I first and the 12 second. So it would be like I, and then multiply by 12. So if you draw the comparisons here, the voltage variables line up, the current variables line up, which means then that the resistance would just be that number 12 that you have there. So you'd have the resistance would be equal to 12, and the unit here says ohms. The symbol for ohms is this this letter. So you have resistance is 12 ohms. Or you could just write down, if you didn't want to write down that symbol, you could write down just 12 OHMS. Okay, last page. Okay, I was going to read this out. It says, in class example 3, the variables I and V are example of continuous variables since they can take on every value within a particular interval. What that means is they're continuous variables because in between values make physical sense. Okay? That's a way I would think about that. So it says, i.e., a variable for which it is possible to find an intermediate value between two values. Okay, so that's a key thing. Do intermediate values make sense? If they do, we call that variable a continuous variable. Now, in class example 2, so that's a toothpick one, the variables P and T can only take on limited values. That's because, again, like when the number of toothpicks was, if we go back here, yeah, number of toothpicks is 4, you'd have 1.5 triangles, which doesn't make any physical sense. So the variables would not be continuous because you cannot have intermediate values. And if you cannot have intermediate values, we refer to those variables as being discrete variables. Okay, and we'll just kind of like summarize this here. So discrete variables are ones where you cannot have intermediate values, or just cannot have any type of value. Or you cannot have some intermediate values. Like there's some kind of intermediate value that does not make any physical sense. Okay, so if you can have intermediate values, we refer to that variable as being continuous. If you cannot have intermediate values, we refer to that variable as being discrete. Okay, so let's label a few of these here. It says classify each of the following variables as discrete or continuous. So let's use D for discrete and C for continuous. So A says the time to complete a 100-meter sprint. Okay, so do in-between values make sense? Like, for example, like could you have 20 seconds? Could you have 21 seconds as your time? Could you have an intermediate value that might be 20.5 seconds? Yeah, sure, of course you can, okay? Like you can definitely have your time to like the nearest tenth of a decimal or nearest hundredth of a decimal. So because you can have intermediate values here, this makes this variable continuous. Okay, the number of students who passed Math 10. Okay, so let's say that you had, I don't know, let's say there's 16 people pass Math 10, 17 people pass Math 10. Let's look at an intermediate value, 16.5. Can 16.5 people pass Math 10? No, because like, what does that mean? Half of a person? Does it mean like just their legs pass Math 10? That doesn't make any physical sense. So in this case, we call that a discrete variable because intermediate variables do not make any sense. Height of a student. Okay, so maybe let's write down some heights here. Look, we could say like, for example, 179 centimeters or 180 centimeters. Could an intermediate value make sense? Could you have like 179.6 centimeters? Yes, you could, okay? Because you could measure the person's height to the nearest like tenth or nearest hundredth of a centimeter if you wanted to. Okay, so we call that continuous. How about shoe sizes? Well, I think most shoe sizes kind of go up by 0.5. So you can have like a shoe size of like 10.5. You can have a shoe size of 10. You can have a shoe size of 11. So it seems at first glance, you're like, okay, yeah, you can have an intermediate value between 10 and 11 because it would just be 10.5. But what if you looked at another intermediate value? Can you have a shoe size of 10.75? Well, they don't really make shoes like that. It's either 10, 10.5, or 11, 10.75, or in between these two numbers, 10.25. They don't make physical sense because those shoe sizes don't exist. So I'd also refer to that as being a discrete variable because not all intermediate values are valid. Okay, so that's it for this lesson. And like I said, it's mainly just a review of plotting points and graphing and just identifying linear relation between different variables, and also just the difference between continuous and discrete variables. So you can practice this by doing on page, right now my pen for a moment chose to lag. Okay, so starting on page, let's go to 394. Do numbers 4 through 6, 8 and 9, and do all parts of these questions. And I'll talk to you in the next lesson.